Welcome back to the Deep Dive. Today we're tackling something huge, really getting into the heart of atomic physics.
We are. We're looking at the quantum mechanical view of atomic structure and spectra.
Yeah, this is like the instruction manual for the periodic table, isn't it? It explains why everything is the way it is, chemically speaking.
That's a good way to put it. Our source material really digs into electronic structure, basically, how electrons arrange themselves around a nucleus.
And our mission today is to walk you through that, step by step. We'll start simple and build up.
Exactly. We'll start with the one case where the math works out perfectly, the hydrogenic atom, and then layer on the complexity needed for, well, pretty much everything else.
And how we actually see this stuff using light, the spectra part.
Crucial. It's foundational stuff. You really can't grasp chemistry or molecules without getting this.
Okay, let's unpack this, starting with the one-electron world.
Right. Hydrogenic atoms.
So hydrogenic doesn't just mean hydrogen, right? It's broader than that.
No, not at all. It's any nucleus, could be helium with one electron knocked off, He plus Ft, or lithium, Li2 plus Ter, even uranium losing 91 electrons. Crazy, I know.
As long as it's got just that one electron left.
Precisely. And the beauty is, with only one electron, there's no electron repulsion messing things up.
So the Schrödinger equation, the master equation, you can actually solve it exactly.
You can, analytically. And the solution, the wave function, it splits neatly into two parts because of the atom's symmetry.
An angular part and a radial part.
Yep. The angular part gives us those shapes that we sort of recognize, the spherical harmonics. These define the basic form of the atomic orbital.
Okay, and these orbitals are pinned down by those three quantum numbers. Everyone remembers those,
Yeah.
hopefully. First is nuller.
The principal quantum number, positive integers, 1, 2, 3, and so on.
Tells you the shell, K, L, M shells, and most importantly, the energy level.
Exactly. And that energy formula is really insightful. It's negative, meaning the electron's trapped, it's bound.
And the energy depends on Zitterwiller, the nuclear charge squared and a squared.
That's right. Numbered on is proportional to minus Ig2 over 2 n. So bigger nucleus, tighter binding, higher light, looser binding. Makes sense.
Then number two, the orbital angular momentum quantum number.
This one dictates the shape of the orbital and the magnitude of its angular momentum. Light legs is an orbital, all like is orbital, less is $2, and so on.
And the rule is go goes from 0 up to beta 1, so no 1p orbitals, for instance.
Correct. Can't have less than, equal to, or greater than 1.
And the third one is $1, the magnetic quantum number.
This tells you how that angular momentum is oriented in space, specifically its component along, say, the z-axis. It runs from a POB through dollars up to plus about.
So for a POB orbital where $1, you get n equal 1 to 0 plus e 0.3 possible p orbitals.
Exactly. Px, py, pt, eventually. Now, the amazing thing is this mathematical framework born from quantum theory, it perfectly predicts the old experimental results. The Rydberg formula, which described the spectral lines of hydrogen-Lyman-Balmer series.
The specific colors of light hydrogen emits or absorbs.
The formula just falls right out of the quantum mechanical energy levels. It was stunning proof.
Total vindication for the theory.
Yeah.
Okay, visualizing these things without pictures. Corbitals, orbitals, the spheres, right? Symmetrical.
Perfectly spherical. And here's a tricky point. The wave function itself, Cirai, is not 0 at the nucleus for sil orbitals. It actually has its maximum value there.
So the electron can be right at the nucleus. Probability density is highest there.
The density, yes. But think about the total probability of finding the electron at a certain distance. That's the radial distribution function, PR.
Okay, how does that differ?
PR is the probability density, SIL-O22, multiplied by the surface area of a sphere at that distance, foldable to 0.
So even if the density SIL-2 is highest at $3, the surface area there is 0.
Exactly. So PR starts at 0, rises to a maximum at some distance.
Which is the Bohr radius, $T, for the hydrogen $1 orbital.
That's the one. And then it falls off again. So the most probable distance isn't 0, even though the density is highest there. It's a balance.
Volume versus density. Got it. And that's crucial because p and orbitals are different.
Fundamentally different in this respect. For p orbitals, the wave function is proportional to 2. For 2 orbitals, it's proportional to 2 orbitals.
Meaning they are 0 at the nucleus, $2 makes them 0.
Correct. They have 0 probability density at the nucleus. They also have angular nodes planes where the wave function is 0. This difference in behavior near the nucleus is key.
Okay, here's where it gets really interesting then. What happens when we add more electrons? Like helium.
Chaos. Well, mathematical chaos anyway. That exact solution we loved, gone.
Why? What breaks it?
Electron repulsion. That $1.12 term in the Schrödinger equation, the repulsion between electron 1 and electron 2, it couples their motions. You can't separate the variables anymore.
So we can't solve it perfectly. What do? Give up?
Huh. No, we approximate. We use the orbital approximation. We pretend, essentially, that each electron lives in its own orbital, described by its own wave function, even though they're interacting.
So the total wave function is just a product of these individual ones. Seems like a big simplification.
It is, but it's the only way forward analytically, and it forms the basis for almost all our thinking about atomic structure.
How do we make it better then?
Computationally. Methods like Hartree-Fock self-consistent field or HFSCF, you basically guess the orbitals, calculate the average field each electron feels from the others, solve for better orbitals in that field, recalculate the field, solve again. You iterate back and forth until the orbitals and the field they generate are consistent with each other.
Self-consistent. Okay, clever. So using this approximation, we start building up atoms, but there are rules, new rules.
Two absolutely critical non-classical rules. First, electron spin.
That intrinsic angular momentum, sort of like the electron is spinning, though not literally.
Right. Discovered via the Stern-Gerlach experiment, electrons have spin quantum number 6 to unpoled to it. They are fermions.
And second rule.
The big one, the Pauli principle. In its deep form, it says the total wave function for identical fermions must change sign if you swap any two of them. It has to be antisymmetric.
Okay, deep. But the practical consequence?
The Pauli exclusion principle. No two electrons in an atom can have the same set of all 4 quantum numbers, honoctors, and the spin projection multimoctors.
Meaning, if 2 electrons are in the same orbital, same dollar now and well, their spins must be opposite. 1 spin up, 1 spin down.
Exactly. Max, 2 electrons per orbital, and they must be paired. This principle is arguably why matter occupies space. It prevents everything collapsing.
And it immediately messes with the energy levels, right? In hydrogen, 2 Legonal or $2 have the same energy. Not anymore.
Not anymore. That degeneracy is lifted in many-electron atoms. And the reason comes back to those orbital shapes and the nucleus. It's penetration and shielding.
Shielding makes sense. The inner electrons block some of the positive charge of the nucleus from the outer electrons.
Right, so an outer electron doesn't feel the full nuclear charge. It feels a reduced effective nuclear charge. Zs is a minus some shielding constant, sigma.
But penetration? That's about how close the electron gets.
Yes. Remember how s orbitals are non-zero at the nucleus, but feet and t-out orbitals are 0 there?
Yeah.
That means an alike electron, even if it's mostly far out, has a small but significant chance of being found inside the inner electron shells, very close to the nucleus. It penetrates the shield.
And when it penetrates, it feels a much stronger pull, less shielding.
Exactly. It experiences a higher ZF momentarily. So on average, an electron feels a stronger attraction than a p electron in the same shell.
Which makes it more tightly bound. Lower energy.
Precisely. That's why for a given one, like 133, the energy order is $3. $3. So it's all about penetration and shielding.
And this order gives us the building up principle, or off-bow principle. Fill the lowest energy orbitals first. $1, then 2 billers, then 2 pairs, then 3 p-pairs, then 3 pierces, the $4 before 3 pairs.
That's the sequence dictated by these energy effects. But then you hit, say, the par orbitals. 3 of them, all with the same energy. Degenerate. How do you fill those?
Hund's maximum multiplicity rule.
The rule of the bus seat. Electrons prefer to occupy separate degenerate orbitals with parallel spins. Before they start pairing up upper para would.
Why parallel spins? Seems counterintuitive, like magnets repelling.
It's quantum mechanics again, specifically spin correlation. The Pauli principle, in its deeper form, forces electrons with parallel spins to stay spatially further apart.
They have an antisymmetric spatial wave function.
Yes. Staying farther apart minimizes their electrostatic repulsion. So the state with the most parallel spins, maximum multiplicity, has the lowest energy.
Wow. Okay, so these rules, Pauli, Hund, penetration shielding, they build the entire periodic table and explain its trends.
Absolutely, like atomic radii. Across a period, Z-day increases because you're adding protons, but electrons are going into the same shell, shielding each other imperfectly. So electrons get pulled in tighter, atoms get smaller.
Until you start a new shell, then the radius jumps up.
Right. And ionization energy, the energy to remove an electron, generally increases across a period because of that increasing Z-lay.
But there are those little dips, aren't there? Like from beryllium to boron or nitrogen to oxygen.
Yep, explained perfectly by the structure. B to B, you're removing the first electron from a 2ka2 orbital boron. which is higher energy and better shielded than the 2A-CLA beryllium, so it's easier to remove.
And O.
Nitrogen has 3 unpaired electrons in 2po upper upper O. Oxygen has 4 upper upper O. That first paired electron in oxygen experiences extra repulsion from its orbital partner, making it slightly easier to remove than expected.
It all fits. What about things like the lanthanide contraction?
Ugh, a great example of orbital effects. The $4 orbitals filled across the lanthanide series are really diffuse shapes. They are terrible at shielding the outer electrons from the increasing nuclear charge.
So as you add 14 protons across the lanthanides.
The Zeph experienced by the outer 6 dozen electrons increases much more than you'd expect. This pulls the atom together, making the elements after the lanthanides, like hafnium, tantalum, unexpectedly small and dense.
Okay, that makes sense. Now, how do we actually measure these energy levels? That brings us to spectra.
Atomic spectra. The lines you see, emission or absorption, correspond to photons carrying energy delta A equal to the difference between 2 allowed energy states, or terms.
Terms, okay. And not just any transition is allowed.
No, you have selection rules. These come from conservation laws, mainly conservation of angular momentum. The photon itself carries 1 unit of angular momentum.
So the atom's angular momentum has to change to compensate when it absorbs or emits one.
Exactly. For hydrogenic atoms, the main rule we learn is delta L equal PM LON1. The orbital angular momentum quantum number must change by 1.
So an electron can jump from SoCal to P to $, or P to $, but not SOP to $, or T to $.
Correct. Those are forbidden transitions, at least in the simplest approximation.
Now, for many electron atoms, it gets more complex. We need to talk about the total state.
Right. We need term symbols. They look complicated, like $2 plus 1 LJ dol, but they efficiently pack in all the crucial angular momentum info for the entire atom's electronic state.
Okay, let's break that down. SoCal is the total spin angular momentum number.
Yes, you combine all the individual electron spins to get a total dollars. The superscript, $2 plus couple 1, is called the multiplicity. $2 plus 1 over n is a singlet state, $2 plus 1 plus 4 is a doublet, 3 is a triplet.
Tells you how many unpaired spins, essentially. Then dollars.
Dollars is the total orbital angular momentum number. You combine the individual dollar values vectorially. $1 is an S term, careful capital S. $1 is a P term, 1, 2 is D, $1, 3 is F, and so on.
And G$ subscript.
Dipl is the total angular momentum number, combining both total orbital and total spin angular momenta. This vector coupling is usually done via the Russell-Saunders coupling scheme, especially for lighter atoms.
So you can figure out dollars, figure out segroballers, then combine them to get possible values of dBl.
Exactly. And the different dBl values corresponding to the same dollar and dollars often have slightly different energies. This splitting is called fine structure.
And what causes that fine structure splitting?
Spin-orbit coupling. It's fundamentally a magnetic effect. An electron orbiting the nucleus creates a magnetic field. The electron's own intrinsic spin is also magnetic.
Like 2 tiny magnets interacting.
Pretty much. The energy of that interaction depends on the relative orientation of the spin and orbital magnetic moments, which is captured by the total angular momentum, $.
So a term like, say, a P term, all more in dollar, with 1 unpaired electron, L2, splits into levels with different gel values.
Right. Dopl can range from $L to $, plus SoCal. So for $L, S12 $2 can be 12 2 or 32 $. You get 2 levels, like 2p12 and 2p32. That's the famous splitting of the sodium D lines.
And this spin-orbit coupling, it gets stronger for heavier atoms.
Dramatically stronger. It scales roughly as Z400. For heavy elements, spin-orbit coupling isn't just fine structure. It's a huge effect that dominates their electronic properties and chemistry. Russell-Saunders coupling starts to break down.
That's a really key point. A seemingly small effect becomes dominant just because the nucleus is heavier.
Absolutely. Now, Hund's rules come back again here, but this time to tell us the relative energies of the different terms arising from a configuration.
Okay, rule 1.
Term with the maximum multiplicity, largest dollar, lies lowest in energy. Again, spin correlation minimizes repulsion.
Rule 2.
For terms with that same maximum multiplicity, the one with the maximum dollar lies lowest. Hand-wavingly, higher dollars means electrons are orbiting in a more correlated way, keeping farther apart.
And rule 3 helps with the dollar levels from spin-orbit coupling.
Yes. For shells less than half filled, the level with the lowest dollars is lowest in energy. For shells more than half filled, the highest dollar is the lowest.
Got it. So term symbols really are the language of atomic spectra. They tell you the state in which transitions between states are likely, following selection rules like delta S equals a caro and delta L equals 0 PMO and delta J equals a 0 EA1.
Exactly. They're incredibly concise summaries of the quantum state.
Okay, let's recap this deep dive then. We started with the hydrogenic atom, the solvable ideal case that gave us the language of orbitals, null LMP, and perfectly matched early spectral data.
Then we faced the complexity of many-electron atoms. The math got impossible exactly, forcing approximations like the orbital approximation and computational methods like Hartree-Fock.
We brought in the non-classical rules, electron spin, and the crucial Pauli exclusion principle, which enforces structure.
And saw how interactions led to shielding and penetration, splitting the Delars PD-SDS energy levels and dictating the Aufbau principle and periodic trends. Hund's rules helped fill degenerate orbitals.
Finally, we connected this structure to observable spectra. Transitions between energy terms give spectral lines governed by selection rules.
And we introduced term symbols, 2 spes plus 1 LJ-DA, to describe these multi-electron states, explaining fine structure via spin-orbit coupling, which becomes critical for heavy elements. Hund's rules helped order the terms, too.
It's a lot, but it pieces together logically.
It does, and it's worth remembering that while the orbital approximation is central, modern computational chemistry goes beyond simple Hartree-Fock to get incredibly accurate results, refining our picture constantly.
So what does this all mean, the takeaway?
It means that these abstract quantum rules, how electrons arrange themselves, their spin, their angular momentum, how they shield each other, these rules dictate literally everything about chemistry.
The size of atoms, how they bond, how they react, how they interact with light. It all traces back to this quantum foundation.
Precisely. The quantum mechanics of the electron is the bedrock of chemistry and materials science.
Amazing stuff. Thank you for joining us for this deep dive into atomic structure and spectra.